Hello, AP Wonders. So, to just address a couple odds and ends from the chapter. So, we are in our Y unit. Really, how does the microscopic, the particle level, that's really microscopic, huh? How does the behavior, specifically the particle attraction between substances, explain why our world is as it is? So, we've already learned that whenever you are asked about a physical property, we need to first categorize, well, what kind of a substance are we dealing with? Is it an ionic compound, a covalent compound made of just nonmetals, or metallic? So we know ionic, made of metals and nonmetals. A single formula unit will be existing in a regular repeating crystalline pattern. Lot of effort to overcome that electrostatic attraction. Ionic bonding extends throughout the whole sample. So we are going to expect very high melting points. In fact, all ionic compounds are solid at room temperature and pressure. Remember, whenever we are dealing with ionic compounds, we're often asked which ionic substance will have the greatest lattice energy. And then, of course, we are employing Coulomb's law. So a reminder of that. Now, if it's covalent, remember, two categories. Is it covalent molecular or covalent network? That's a whole different categorization. Covalent network, the short, very strong covalent bonds extend through the entire solid. So in your unit packet, that is our categorization that we give to diamond, graphite, silicon dioxide, silicon carbide, extraordinarily hard, very high melting points. These are the strongest solids. That covalent bonding extends through the whole sample, so it's like you have one ginormous macromolecule. Metallic, of course, sea of electrons that are responsible for all the unique properties of metals. If it is covalent molecular, so if it is not diamond, graphite, silicon dioxide, silicon carbide, well, then we could be under these intermolecular force categories. Remember, we ranked from quote unquote weakest to strongest, realizing, okay, there's going to be some range. Covalent network, absolutely strongest kind of particle attraction. Ionic range, metallic range. Then there is a huge separation. If I could, the intermolecular forces really belong kind of, roughly 6 or so percent weaker. So there's a big divide here. Ion dipole, the strongest of the intermolecular forces, and so on. Now, I really wanted to make sure that we understood the relative strength, but that we know when we're going to be encountering the diagnoses for these different particle attractions. When do we know? Well, ionic, it of course is going to be a formula made of a metal and a non-metal. We know that. Covalent network went through the special handful, any other non-metal combination, and then of course metallic. All right. But the intermolecular forces. So, ion dipole. That is when we have soluble ionic in aqueous solution. Great example. And that is where we're going to have our full cation that will be attracted to the polar, so we just say the dipole of the water molecule. Hydrogen bonding, already went over that. So that is where we're going to have polar molecules that can create that hydrogen sandwich. And so on one molecule, either hydrogen bonded to fluorine or oxygen or nitrogen, and then On the other molecule, do we have a fluorine or oxygen or nitrogen? So that will be what we're looking for. That one side of bread is fluorine, oxygen, nitrogen, the other fluorine, oxygen, or nitrogen with a hydrogen bound to one of those. Dipole, that is going to be between a polar and a polar, but it is not as strong as these because of the electronegativity difference that these elements create when they're bonded with hydrogen. Ion-induced dipole. So we do have some ionic compounds that are soluble in polar solvents. So for example, sodium hydroxide may be in methanol, which is a polar solvent. Yes. And so I'm sorry, I just hesitated for a moment. And so we're going to have, oh, forgive me. Am I saying? So ion-induced dipole, oh, it would be something soluble ionic that would be in a non-polar solvent. And so we could see that ionic compounds are going to induce a dipole. So let's say that we do have that sodium ion and we have a non-polar molecule, but one especially that has lots of electrons. Well, this very positive could encourage, induce, persuade, if you will, the molecule because of the particle attraction that can form. Then that electron density is going to hang out here a little more. And so we could get, now it's going to be a very, very small partial charge, but that ion could motivate, because of the lowering of energy, this electron density to be found more often here. So ion-induced dipole would be between like soluble ionic that will dissociate and then non-polar solvent. Dipole-induced dipole, that would be polar with non-polar. And so something like this, we might have a polar molecule that would have a permanent dipole, but then we have a non-polar where we have the fluctuating dipoles, relatively small because of traveling electron density. So this permanent dipole could encourage this to show the positive. And so non-polar is encouraged to be a little more polar than it normally is, or to just keep the fluctuation to a minimum. All right. The London dispersion, of course, between non-polar and non-polar. So we definitely spent some time making sure that we know, okay, if we're asked to rank boiling points or why something would be more soluble in water than another, that we can definitely diagnose our species we're dealing with. All right. So then we revisited this relationship. So in our unit packet, we already have talked about viscosity. We said we recall surface tension, capillary action, but what exactly is vapor pressure and then enthalpy of fusion, enthalpy of vaporization? And so in our unit packet, toward the back, there are some images. And if you want to pause, this is page 19 in your unit packet, and really take in what this is showing us. Increasing enthalpy, heat content, if you will, solid, transitioning to liquid, transitioning to gas, melting, and then vaporizing. The delta H standard of FUS, that is the enthalpy change at standard state conditions. Fusion is melting. So this is enthalpy of melting, if you will. So it is the heat energy required to transition 1 mole of a solid to its liquid state. Now, the requirement for the heat investment, and it's going to be positive, of course, we're moving upward in the enthalpy content. This is a lower value than vaporizing. So this would be the heat required to vaporize, and usually it's kilojoules per mole, 1 mole of your liquid, where we know particle attraction is approximately equivalent to kinetic energy. Well, we need to overcome the particle attraction. So it's a much greater investment of heat, where here we are just, here the particle attraction is greater than the kinetic energy, and we're just trying to allow for these to be a little more equal. All right. And of course, sublimation would be transition right from the solid to the gaseous state. Well, in this direction, these are the opposite changes. Notice they are the negative or the opposing sign of the opposite, if you will, phase change. So when we condense, it's negative delta H of vaporization. When we freeze, it's negative delta H of melting or fusion, and so on. And of course, different substances have different quantities of enthalpies of vaporization and fusion. So again, kilojoule per mole. For example, water, we know, shows hydrogen bonding versus methane, just London dispersion. So we would anticipate, if we did not know what these substances were, that much higher particle attraction than these at this end. And we're always seeing enthalpy of vaporization is a greater required investment of energy versus enthalpy of fusion. All right. Just a reminder of Maxwell-Boltzmann distribution, that temperature is a measure of the average kinetic energy. And at a certain temperature, you're going to have some particles at a greater speed and a lesser speed, or a greater kinetic energy and a lesser kinetic energy. So we don't want to confuse peak with greater temperature. We look at the average. So this orange sample shown here, it has a greater average. So that's our higher temperature. All right. We know if something is existing in the liquid state, that there is particle attraction, be it London dispersion or possibly electrostatic in the case of a liquefied ionic compound. So we know that the particle attraction will be pulling in every direction. So this particle is pulling on all the surrounding, but then being pulled by. Of course, at the surface, these are just pulled sideways and downward. That, of course, is what creates our surface tension. And the greater the particle attraction, the greater that force that needs to be broken because of that top level particle attraction. Well, we understand that if we have liquid, well, some of those particles are going to get enough kinetic energy to overcome the particle attraction and become vapor. But if this beaker is open to the classroom, well, we know there's also, for example, nitrogen and oxygen, and that will be behaving as gas and colliding with the surface of the liquid, the walls of the beaker, just as the vapor that's coming from the liquid. Well, that is what creates vapor pressure. Vapor pressure. Vapor pressure is the pressure a vapor exerts on the liquid it vaporized from. The others are just exerting gas pressure. So it is only because of the vaporization from the liquid. Now, the greater the particle attraction, the lesser the concentration of gas that will be formed. So we have to remember this is an opposite relationship. The stronger the particle attraction, the lower the vapor pressure for that substance. So these substances at any given temperature have different vapor pressures because of their different particle attractions. So if we choose a temperature, let's say 40, we encounter water here, ethanol, and then diethyl ether is off the chart. But comparing these, at this temperature, we'll have less vapor, so a lower pressure from that vapor, because water has greater particle attraction than ethanol. We could definitely make that connection. Do we see, though, vapor pressure always increases with an increase in temperature? No matter what, we can depend on that. So just a little more graphics with that. And I think that was about, what we have covered. We need to still address warming curve and then alloys, but that is what we addressed and looked at some sample questions in class. And we will continue on this wonderful adventure of answering the why of our world by being able to diagnose what kind of particle attraction is present in the substance.